Okay, good morning, everybody. First of all, I would like to thank the organizers for inviting me to be here and to share the celebration of Sergio Vitanti. And looking at the topic of my talk, I'm going to deal with a similar problem, but in a very different perspective. So I'm going to deal with disturbances, trying to identify, to know about them, and to reject in some very simple cases. There is no... Okay. So this is the content of my talk, a brief introduction, and then when you can measure the disturbances, you can apply feed-forward control. If not, you can go to estimate the disturbance by different approaches. Disturbance observer, uncertainty and disturbance estimator, and active disturbance rejection control. I will plan to go very briefly on all these approaches, and in the end I will make a comparison about So if you have a plant, you can consider this kind of disturbances. First, there is output, internal or input disturbance, and then under the ideal control, you want that the control is such that the output is following the reference and without effect of the disturbance. So we split the control action in two parts, the control for the tracking and the control for the disturbance rejection. And then we can also consider internal disturbances, as we will see later on. That means that these models of the plant are not precisely known. So there are many approaches to deal with the problem of disturbances, and one of them that I'm not going to consider here is the robust control, in the sense that you are trying to design the control in such a way that the disturbance effect is under control or limited, at least. So the idea here is we can deal like in the PAD approach, looking at the error and trying to minimize the effect of the disturbance. Then in the case of the academic approach, you need to have a good model of the plant and also the disturbances. And in the disturbance rejection approach, they combine both, the plant model and observers for the reaction control. So as I mentioned, we are trying to get information from the disturbance and trying to generate a feed-forward control to attenuate its effect. So the approach I'm going to consider here is the feed-forward control, just in case that you are measuring. And this is the relevance of getting information from the plant, identification, not only the model of the plant, but also the disturbances. And then we will go for the disturbance observer, which is unfortunately only applicable when the model of the plant is linear. Then we will go to the uncertainty and disturbance estimator, when we are assuming a basic behavior, and all the disturbances and all what we don't know are put together in a lumped signal that we try to estimate and counteract, including non-linearities, which is the main difference with respect to that one. And then I will say a few words about what is presented nowadays as a panacea for solving the problem of the disturbance, which is the active disturbance rejection control. It has many followers and many applications on this technique, but we will see that something is not clean for me in this approach. So in the case of the feed-forward control, we assume that the disturbance is measurable or estimated, and then if we have this equation for the output, the clear idea is that the control for the disturbance should be such that this term is cancelled. So it's a perfect cancellation if this control here includes the inverse of the model of the plant. So, for instance, in a very simple example, we have this model for the input and this model for the disturbance. And then the feed-forward controller should be, if you just try to control the static behavior or static with a delay, or if you want to cancel the dynamics also. And then for the feedback controller, you will use, for instance, a PI. So these are the evolution of the output when we are using feed-forward controller, and in open loop and in closed loop. And you can also estimate the disturbances. So let's move to the disturbance observer. And we arrange a couple of filters, Q1, Q2, in such a way that this signal, the control for the disturbance, can be expressed like Q1U plus minus Q2Y. So we are using all the information we have from the plant, and we are assuming that no one of these disturbances is measurable. So if we do that, then and we put together with the model of the plant, we get to this expression here. And you see here that in some cases, we can get that Y, it depends only on UC, if all these terms can be cancelled. So let's see situations. So if the model of the plant is minimum phase and its inverse is realizable, so this exists and is stable, then if we choose Q1 equal 1 and Q2 equal the inverse of that, then the output is given by the undisturbed model. So if we put Q1 equal 1 and Q2 equal the inverse of this in this scheme, then all this is cancelling all the disturbances here. So if the inverse is not realizable, as is usually the case, then we need to introduce a filter, Q, in such a way that Q1 is equal Q and Q2 is the same as before but multiplied by Q. Then the output is not anymore just the clean input to control relationship, but there is this term. So all the disturbances are filtered by this term. As far as this term is 0 for the range of frequencies of the disturbances, this is still a nice and a clear solution. So if the plant is non-minimum phase, and let me assume that there is only one process, and the process is split into the positive and negative, the non-minimum and the minimum phase part, then we can, again, find a nice solution, but in that case, Q1 should include Q as the non-minimum phase factor, and Q2 is the inverse of the invertible part of the plant. Then if we use these two filters, the solution is like this one. So in that case, we can choose the filter in such a way that this term is 0 or near to 0 for the range of frequencies of the disturbances. We can also deal with time delay plants, but in that case, the filter is like this one. And then we can cancel the effect of disturbance, but we cannot cancel the effect of the delay. So as a conclusion, in the disturbance observer approach, it's only applicable to nonlinear plants, and if there are time delays, they are unavoidable, and only steady-state disturbance rejection can be achieved. One interesting question is what happened with the internal disturbances? We can consider the internal disturbances as a mismatch in the model, and then this mismatch can be expressed as the difference between P and G. And then if we apply the small gain theorem between this point and that point here, we realize that the system with this loop as before is stable as far as this condition holds. Then that means that there is a constraint in the uncertainty. The uncertainty cannot be very large, and the sign of Q is based on this uncertainty. So this is another very simple example that I guess that you are going to forward the slides to the audience so they can follow the examples very. Okay. Okay, let's move to the another approach, which is the uncertainty and disturbance estimator. The proposers of this approach also say that this is fantastic and solves all the problems. But the main difference with the first approach is, first, it's stated in the state space form, but it allows for nonlinear terms. And then we assume that we want to find a control to reach this closed loop behavior. And the control goal is to get an approximation error, which is going to 0. That means that this term should be Hurwitz. As we will see in a few slides, this requires a structural constraint, what is called a matching condition. And the nice thing is that it's applicable for nonlinear systems, but also for MIMO plans. The DOB was only for a single input, single output plans. If we subtract the model of the plant and the expected model, the design model of the plant, then we reach to this error evolution. And in order to cancel the disturbances and uncertainties, the control should be such that BU should be equal to gamma. And then the control to cancel the disturbances will be such that this. And then you see here that this requires that the control is obtained by the pseudo inverse of B multiplied by all these terms. So all these terms should be in the rank space of B. This is what I have called before the matching constraint. And if you look at the UD can be computed like this, but of course this is not accessible. So they are using a filter, and based on this filtering, they design the control. So here there are two, from my point of view, there are two issues. First of all is that all these terms should be in the rank space of B to be computable. And second one is this filter, JF. And this filter, in the case of the linear systems, is in some way related with the Q filter that we have seen before. But nobody has explained the neat relationship, and we are working with that. So what is the structural constraint? The structural constraint is that this gamma should be in the rank space of B, but if you look at the idea of gamma, you see here that the disturbances, the uncertainties, and the nonlinear terms should belong to the rank space of B. But of course there are many nice and simple examples that illustrate this design. And for instance, assume that we have this system with this nonlinear part. This cannot be treated with the disturbance observer because we are dealing with nonlinear terms. So if we assume that the model we want is that one, then we use a simple low-pass filter, like this one, and we select the time constant of this pass filter, and we assume that the extra matrix Ka is equals 0. Then you can see that we are applying here a disturbance, and the disturbance is almost rejected. So the solution is very good. And you can also estimate what is the disturbance that you have been applying in the system. In the case of the ADRC, the approach is a bit different. We assume that the plant is nonlinear, and the plant can be represented in the chain of integrators, like this one. And the disturbance is only applying to the last state variable. So in that case, we assume that we introduce a new state variable, which is the derivative of the disturbance. And we create this extended system. By this extended system, augmented system, we introduce a estimator, a Leuenberger extended state estimator. L is the selected to provide an adequate estimator of the disturbance. And then we control. Once we have estimated the disturbance, we apply the control just to cancel the effect of the disturbance. And then we remain with a chain of integrator, which is the ideal one. So the design procedure is we get a suitable representation like this one. Then we extend the state. We design the observer gain. And we design the control for the chain of integrators. Of course, here, the key issue is the observer gain, other than the representation in this form. And we guess that this observer gain is related with the GF filter before and with the Q filter in the DOB in the case of the linear systems. So we consider the same system as before, and the solution is practically the same. So either with the ADRC or with the EUDE, the solution is very similar in both cases. In fact, the simulations were the same. So as a conclusions, we always have disturbances, external and internal, and they should be considered in any control applications. If the disturbance is measured, and we have a good model of the plant, then feed-forward is the best option. Otherwise, we should estimate the disturbance if it cannot be measured. And it depends very much on the plant dynamics, how we can estimate the disturbance. As I had said before, DOB works well for linear systems, including delays. EUDE deals with MIMO nonlinear uncertain systems with some structural constraints. And IDRC also deals with these systems and generalizes some previous results. Currently, we are dealing with working on the time-delayed plants with considering the zero dynamics. And also, two open questions for me are, what is the robustness of the IDRC and the EUDE with respect to the uncertainty in the model, and also what is the relationship between the filters Q, GF, and the Leuenberger observer in the last design. But in any case, we think that we should try to estimate the disturbances and try to reject them if possible. And this is an advice also for Sergio in the next time of your life. You should try to detect the disturbances, estimate, and look for rejecting them in such a way that you will have a very joyful, long life in the future. Thank you.
Thank you very much.